Hi, my name is Sebastian Baltes. I'm a lecturer here in the School of Computer Science, and I'm giving a guest lecture in the search-based software engineering course about our open dataset SOTorrent, which is based on official data that the Stack Overflow platform provides. What we did is we reconstructed and analyzed the evolution of content on Stack Overflow. This work has been published in two publications, one full paper at the Mining Software Repository Conference in 2018, and in the following year, the same dataset was also the official mining challenge of MSR, and you'll find more information about the dataset and also preprints of those papers on this website. So what is Stack Overflow? I guess most of you have heard of Stack Overflow or used Stack Overflow. It is a question and answer website for software developers. It covers a wide variety of programming related topics. Posts can be commented, edited, and downvoted on Stack Overflow. It also has gamification features through reputation points that users can earn depending on their contributions on the platform. And Stack Overflow also has a section for job advertisements where employers can advertise their openings in the domain of software development. As of June 2019, there are over 10 million registered users on the platform and almost 18 million questions. This is how a typical Stack Overflow thread looks like. So you have a title here, then a question that some user asked. The question can be upvoted. You have information about who asked this question and whether the question has been updated or edited. There are comments here and linked resources, and further down you have the answers to this question. Let's look at one answer to this particular question. Those answers often contain code snippets. This is a rather short code snippet. Some answers contain whole classes, for example. Some others methods, as in this case, and others just a couple of lines or very short code snippets. Another thing that I wanted to mention is that those posts often contain links to external resources, and edits are sometimes documented in the posts, but we'll look a bit closer at this example later. First, I want to motivate why we did this research, why we reconstructed and analyzed the evolution of such posts. First of all, it happens. So posts are updated, edited after their creation. When we started working on this data set in 2018, over 14 million posts were updated, edited after their initial creation. Today, it's likely many more. And like other software artifacts, Stack Overflow posts evolve over time. Bugs are fixed in code snippets, but also clarifications are added to the text around those code snippets, and often both is done at the same time. So code snippets are fixed, updated, and then at the same time the edits are then clarified or documented in the surrounding text. And sometimes snippets are also updated to new language versions. For example, after the introduction of lambda expressions in Java 8, these snippets were updated to contain variation that uses those lambda expressions. Another aspect to this is that copying code from Stack Overflow, for example, into open source projects on GitHub, is very common despite all licensing, security, and maintainability implications. We actually had related research project exactly about this, about the implications of copying code from Stack Overflow into projects, especially from the licensing perspective, but this is not the focus of this talk. We will focus on the evolution within the platform. There are also differences between how code on Stack Overflow evolves in relationship to code on platforms such as GitHub. For example, the code on Stack Overflow is usually rather short. In our research, we found that it's 12 lines of code on average. There is no tracking system on Stack Overflow. You only have the comments that you saw earlier, or users can post alternative answers and then mention that in another answer in the same thread there was some issue. There's no versioning for individual code snippets on Stack Overflow, so the versioning is done on the level of whole posts, not the individual snippets and text blocks that you saw in the earlier example. Let's go back to that example to have a closer look at the different aspects that you see in such a Stack Overflow answer. I mentioned the code snippets already, and I mentioned links, in this case to an external source where an earlier version of the snippet has been taken from, and then it evolved further on Stack Overflow. There can also be links to reference documentation, such as the JDK in this case, and post edits are sometimes documented in the posts themselves, and then reasons are provided why the snippet has been edited in this case. If you look at comments, the situation gets even more complex because there can be bug reports in the comments, as in this case. Sometimes users even post alternative solutions in a comment instead of posting a new answer. And the original author of the answer, he also commented here and mentioned that the snippet that he's providing is clearly a hack. So this is quite interesting because hidden in the comments, the user acknowledges that his solution is clearly a hack. And if you see just a snippet and the text surrounding the snippet and the other answers in the thread and the question and so on, it's not immediately clear that it's just a hack. So users may just, users of the Stack Overflow platform may just see this snippet, copy it, use it, without knowing that it's clearly a hack. Another aspect is that the snippet is based on an external source. It's further evolved on Stack Overflow, which makes the whole evolution and also the licensing situation, of course, very complex. I pointed to the bug reports in the comments. So there are issues with the snippet, or there were issues with the snippet that have been fixed, and it's just not clear whether they have been fixed or not. And also, it's unclear whether the snippet is safe to use because the author himself mentioned that solution is clearly a hack. And our dataset tries to help researchers addressing two of those aspects, namely analyzing external sources for snippets by providing easy access to the links in the posts. And it also enables researchers to analyze the evolution of content on Stack Overflow and the edits to code snippets and the surrounding text blocks, etc. Going to talk about this the remainder of this talk. Stack Overflow itself provides a revision view where you see basically all the revisions of posts, all the edits that have been made. But there are several problems with this. The history is only available on the level of whole posts. As you see here, it's not available for just the code or just the snippet. It's always the whole post that is being versioned here. So in this case, there were edits made to the snippet, but also to the text. Therefore, it's hard to trace the evolution of an individual snippet because it's hidden in this evolution of the post here. There are edits that may have not changed the snippet. Then also comments and edits are not linked in any way, so if we see an edit here, we don't know whether it fixes one of the issues outlined in the comments, except for when the user added information here in this message referring to a certain comment. And it's in general unclear how external resources are related to the edits and also to the code on Stack Overflow, but it's not so much a problem of this revision view, but more Stack Overflow in general. And what we would like to have is the evolution on the level of individual blocks. So text and code blocks. Code block is always this part here with the gray background, and the text blocks surround those snippets. And we would like to have this level of granularity, level of blocks and not of posts. And this is why we built the SOTorrent dataset that provides more fine-grained evolutionary information about the Stack Overflow content. So our dataset is based on the official data dump that Stack Overflow provides, and it addresses some of the issues I outlined earlier. So I mentioned the issue that the version history is only available on the level of whole posts, and in the torrent dataset, we reconstructed the evolution for individual post blocks, so text or code blocks. And this allows you to analyze the evolution of individual code snippets. It's possible in the SOTorrent dataset. And the dataset also provides links, information about links from posts to external resources, but also from GitHub repositories to Stack Overflow posts. I will show you some examples later. Using simple SQL queries, it's pretty easy to retrieve all versions of a certain code snippet. So this is the code snippet from the example you saw earlier. And using the ID of the post and the so-called local ID, we can simply retrieve all the different versions of that code snippet. So the local ID is basically just a number assigned to all blocks in a post. So this text block has local ID 1, this code block 2, and this text block 3. It's just a numbering within the post. And we can use this in queries. And you see here the complete version history for this snippet. And here you see that the snippet actually has been changed a couple of times. And when you look at two specific versions, in this case, the two most recent versions, you can also retrieve information about which lines were changed. So you can retrieve a line-based diff between post blocks using the dataset. To be able to execute such queries, we had to reconstruct the version history of Stack Overflow on the level of post blocks instead of whole posts. And the first step in doing this was to extract the post blocks from a post. Again, this is the example shown earlier. This is how an answer is rendered on Stack Overflow's website. But actually in the data dump, the source is in the markdown format. This is how how this post looks like in the source code basically. And this is then rendered on the website as this. And what we would like to have is this layout, as I mentioned. Text blocks, code blocks, the local IDs here you see 1, 2, 3, text, code, text, Yeah, and then the content of the text block, of the code block, and of the second text block here. This is the structure we need to be able to retrieve the version history also for individual snippets that are then isolated here as individual code blocks. So in a perfect world, it would be easy because in the Stack Overflow Markdown specification, it's mentioned that code blocks should be indented by 4 spaces. And if a text is indented by 4 spaces, it's displayed on the website as code. But Stack Overflow also supports other Markdown conventions, such as the GitHub Markdown specification, but it also supports different HTML tags that are correctly rendered on Stack Overflow's website. Therefore, we use an iterative approach to reverse engineer how Stack Overflow renders certain ways of highlighting code snippets. To this end, we randomly selected 100,000 Stack Overflow posts. We then implemented a certain extraction technique, starting with the indented layout that Stack Overflow recommends. Then we checked a random subsample of those posts and verified whether this structure is the result of the extraction process. And when we found violations, so code snippets being detected as text blocks and the other way around, we added test cases reproducing this behavior, reproducing the issues, then updated our extraction method until all test cases passed, and then triggered the extract again, looked for examples where there were still issues with the extraction, and again writing test cases, updating the methods, and then triggering the extraction again. And we did this until we didn't observe any new violations of the structure. I briefly wanted to mention that Stack Overflow publishes their Markdown editor and their Markdown processor, but we couldn't really reproduce how posts are rendered on the Stack Overflow website, and also those repositories were rather outdated. So we suspected that this is not the most recent version of how things are being rendered on Stack Overflow servers. Therefore, we had to rely on this reverse engineering approach I just outlined. So in the end, we observed many different variants of highlighting code on Stack Overflow, including the official indentation by 4 spaces, GitHub's way of highlighting code using 3 backticks. There are also so-called Stack Overflow stack snippets that are rendered a bit differently on the website, and HTML code and script tags that were also quite frequently used. Oops, sorry. And the code we use to extract the snippets or text and code blocks from Stack Overflow's Markdown source can be found on GitHub if you're interested to have a look at the source code of this extractor. After extracting the text and code blocks, we had to match the individual blocks to their predecessor version, to a block in the previous version of a post that matches this snippet or the text block. And this is an example that illustrates this issue. For example, in the first version, you may have this text here, this text block, as first text block in the post, and then in the next version, this text block is being slightly modified, and those should be matched, of course. Here is a new code block that was not there in the previous version, and obviously this one doesn't have a predecessor then. And those code blocks have not been modified. They should be matched to each other. The same for the small text blocks here, the labels from client, from server, etc. And this shows already that it's not always trivial to match those text blocks because there may be multiple candidates to connect. This is more of an abstract view on the problem outlined in the previous example. So we have one text block, the first text block that has been slightly modified. This is relatively easy to match. We have a new code block that doesn't have any predecessor. It's also easy. We don't need to set any link. But then we have multiple candidates. We have text blocks with the same content in both versions. And yeah, it's unclear which exactly is the predecessor of the text block in the newer version. One strategy we followed is to treat the text blocks as labels for the following code blocks. And when we consider this, when we take this into account, we can map the text blocks because the code blocks didn't change and the labels stayed the same. So we can use that information to not set the predecessor for this text block, but for this one. This is just one example, one case that is meant to motivate why it's not always trivial to set those predecessors and that we need some strategy to deal with this. This is the predecessor selection strategy that we implemented. This is pseudocode. And in the next few slides, I'm going to introduce the notation that we need to fully understand this matching strategy. The thing is that when you have just one predecessor in the preceding version that matches a certain, in this case, text block in the next version, and also this text block in the previous version doesn't have any potential candidate here that could be linked to. So when you have a unique match between those, it's easy. We don't need to do any selection. We just link those two. But as soon as we have more than one candidate as a potential predecessor of a text or code block, as in the case I outlined here, we need some strategy to select from those candidates. And this is what this matching strategy is about. Considering the context as illustrated here is one part of the strategy, but there are also other aspects. Considering the context is exactly what I just mentioned, looking at existing links or at surrounding blocks that already have a predecessor and considering this information to make the decision, but it's not always possible. Therefore, we also have a fallback strategy that works based on the position. So that tries to match the post blocks that are close considering the local ID. So local ID again is just the numbering of the blocks. So this is local ID 1, 2, 3, 4, 5. Here's 1, 2, 3, 4, 5, 6, 7. And if we have multiple candidates, we look at the difference in the local ID and select the block that is the closest to the one we want to match. That's our fallback strategy. But to fully understand this strategy and the notation used, we need some definitions that we're going to introduce in the next slides. And the goal is to establish a linear predecessor relationship for all versions of a post block. So we don't want to set more than one predecessor for a certain post block. And we made that decision because then the data set is much easier to store in a relational database. And also we very, very rarely observed splits and merges of blocks. And even if we observe a split of one block into two parts between versions, usually one part is much larger than the other, and it may still make sense to connect the larger part to the predecessor, and then we can keep the linear predecessor relationship that we try to establish. And as I mentioned, we need some strategy to decide between multiple candidates for a predecessor. And to understand that strategy, we need some definitions. First of all, we need to define a post version, and we define a post version as PI in this example. So if we have a post P with n versions, PI is version I of that post, and the cardinality of PI is just the number of post blocks within that post version. So PI is just this, for example, this is version 2 of the post, and this is P2 then, that specific post version. N is the number of versions that we already saw in the revision view in the example earlier, in this case 15 versions. And the cardinality of P2 is 3 in this case because we have 3 blocks, 2 text blocks, 1 code block here. And then we need to define a post block version. So if we have PI, version PI, P2 in this case here, we introduce tau as the type of this, of a particular post block, and the type can be text or code, as we also see here, and so tau can be text or code, and this is the post block type in our notation. And then if we write b tau il, this means we have a post block of type T, for example, a code block would be b code in version I with local ID L. This is how we read this notation. And the local ID is of course from the set of 1 to cardinality of this specific version, meaning the number of post blocks in that version. We also define a function ID tau that maps for a specific type, text or code, that maps to the local IDs of that type. So for example, this text block has local ID 1, this has local ID 3, and this code block has local ID 2, and then the ID function, depending on tau, maps to 1 and 3 or to 2 for the code blocks. Yeah, exactly. This is just an example. So that L refers to local IDs 1, 2, 3. And in that notation, we would identify this text block here, the first text block, as b text21 because it's version 2 of this post and it's local ID 1 and it has type text. Code block is b code22 because it's version 2 of the post and the block has local ID 2. And this text block is 2.3 because it's version 2 of the post and local ID 3. So now we have a way to uniquely identify the post blocks within the post version of a post. And as I mentioned earlier, our strategy is about matching a post block to a predecessor in the previous version. Therefore, we want to define a set of possible predecessors that we want to select from using our strategy. So we look at post blocks in two versions, version I and I-1. So this is the previous version, this is the next version. And of course, we always compare blocks of the same type. So with the same tau here. Then we define function equal as true if those two blocks have the same content, and false otherwise. And you see here those blocks don't have to be the same position, don't have to have the same local ID. Local ID can differ, but the type tau should be the same, and it should be one version I and the predecessor version I-1. So in this case here, where the first text block was modified, slightly modified, the newer version, the equal function for those two text blocks would yield false. For code block C1 here, that is equal. If we compare those, the equal function would return true. Similar to the equal function, we also have a similarity function, tau. So the similarity function is available for the two different types. So we have different similarity functions, one for text blocks, one for code blocks. When we apply this similarity function to those neighboring post blocks, the similarity function yields a value between 0 and 1, just quantifying how similar two posts are. We will talk about the different similarity metrics that we used for our implementation, or that we evaluated for our implementation in a couple of slides. Yeah, you see here that, for example, if we look at text blocks, those would be the blocks that we can compare to each other using the equal or the similarity function. We also need a similarity threshold that we use to select predecessor candidates that are similar enough to be considered as a predecessor. And as I mentioned earlier, we have two similarity metrics, one for text and code, and therefore also two thresholds, one for text, one for code. We can now define the set of equal predecessors pred equal, which is simply for one post block, all post block in the previous version that are equal to, that have the same type and that have equal content. Then we also define the maximum predecessor similarity, maxim tau, as the maximum similarity of blocks in the previous version of the same type that is above the similarity threshold. Now that we have all those definitions, first I wanted to mention that, of course, maxim, the set can be empty if no predecessor has a similarity above the threshold, and then we simply define maxim as 0. The set of matched predecessors is simply defined as all blocks in the previous version of the same type that have the maximum similarity according to the similarity metric. And of course, this can be true for more than one predecessor. Yeah, and we ignore the cases where there was no candidate above the similarity threshold. And now finally, we can define a set of possible predecessors pred for a certain block as the set pred equal if we have an equal predecessor, or the set pred matched if pred equal is empty. So we always try to select the predecessors that have same content before we apply our similarity metric, and only consider the similar but not equal predecessor candidates. And this is because similarity 1, according to some similarity metric, is not the same as equality, depending on how the similarity metric is implemented. And we observed that it's important to make that distinction to improve the performance, distinguishing those two cases, actually having equal content or having similar content according to some similarity metric. Okay, now that we have this set of possible predecessors for a certain post block, we have to select a candidate according to a strategy. This was the initial motivation why we introduced all those definitions and why we presented the matching strategy. And as I mentioned earlier, we have basically two main strategies, one using the context around a certain block to determine which predecessor to select, and the backup strategy just considering the position according to the local ID. And both matching strategies just iterate over all post blocks in a certain post version that do not have a predecessor yet, and try to set one according to the set of predecessor candidates. And the context strategy looks at the blocks with local ID +1, -1, starting from the block we are currently considering, and then basically looking at those neighbors and seeing whether they already have a predecessor in the previous version, and whether the block that we are considering that is in between those neighbors could be a potential match for the block that is in between those other two blocks in the previous version. And this is exactly the example that we saw earlier, that when we know that those two code blocks are connected, C1 and C2, and the text block is not connected yet because there are multiple candidates, we can set this connection because we have the context around that link. We also implemented variants of this strategy where we only consider the links above or only the links below a certain block. So whether we only look at this link here and then determine if this link is present, if this is our candidate, or whether we only look at the block below, see whether we have a link here, and then decide on the candidate. The other backup metric, as I mentioned, just looks at the local ID and tries to select the block that has the most similar local ID to the one we have in the more recent version. And if two candidates have the same local ID difference, we select the smallest one. So if we have a candidate that has local ID 1, we have a candidate that has local ID 3, and in the next version, it's local ID 2. The difference is the same, it's 1 for both. Then we would select 1 as a candidate. And this is again motivated on examples we looked at, and we saw that the order of post blocks rarely changes. And if it changes, usually the blocks stay very close to where they were in the previous version. Okay, now we can briefly go over the actual matching strategy now that we introduced this notation in the different strategies. And what we simply do is for all post versions starting with version 2, we look at matches in the previous version, and for all blocks in this version, we determine the set of predecessor candidates. And if we only have one potential predecessor in the previous version, and if this predecessor only has one potential successor, then we simply set this predecessor, because then we have a unique match. We don't need any sophisticated matching strategy. We only have this candidate. We can safely set it. It's fine. If that's not the case, we first apply the context matching strategy, looking at the blocks above and below the current block. And if this is not successful, we ignore the block above. And if this is also not successful, we ignore the block below. And then finally, if that also fails, we set the remaining links using the position, the local ID difference as outlined below. And all this, so also the order of this, first considering both, then below, then above, is all based on the examples we looked at, the test cases we implemented. So it's not just a random decision we made, it's based on examples we looked at. And after we implemented this, after we evaluated this, we looked at the false positives and false negatives resulting from this matching strategy, and then refined the matching strategy I just presented again. So the matching strategy that is currently being used to extract this information from the Stack Overflow dump is even a bit more complex than what I just described, but I won't go into detail in this talk about the revised matching strategy, because you see here that the general strategies, like using context, for example, is still applied. But we managed to considerably improve the performance using this revised strategy. And I wanted to mention that, of course, we need the similarity metric and the thresholds as outlined earlier. And those similarity metrics, the thresholds, and the strategy are closely related. So it's very hard to evaluate just one of those, just a strategy independent of the metric or the other way around. And what we did is testing our strategy with different similarity metrics and seeing which of those performed best. So performed best in terms of runtime, but especially in terms of reducing the number of false positives and negatives. We implemented many different similarity metrics like Levenstein distance, also cosine similarity, similarities based on n-grams, etc. And if you're interested in this, the source code is again available on GitHub, and those similarity metrics are implemented in Java. We implemented all those metrics ourselves. Yeah, and we had to rely on basic text similarity or string similarity metrics because we cannot assume anything about the content in Stack Overflow posts. So even if it's a code snippet, it may contain bugs, it may not compile. Therefore, we cannot use more sophisticated ways of comparing the content. Therefore we had to rely on basic string similarity metrics that work regardless of the actual content. We developed a small tool to create a ground truth for our evaluation, where we basically manually annotated the version history of 500 posts. So we manually annotated which blocks should be connected with each other and which not. And then we use this as a ground truth for the evaluation of our matching strategy and the corresponding string similarity metrics. This these are the results for the first part of our evaluation. Before we implemented the revised matching strategy, we already achieved a true positive rate of 99%, both for code and text. But we still have a false positive rate for text of 14% and for code of 7%. But still, the Matthews correlation was pretty good for code 0.92 and for text 0.86, and we were able, using the revised strategy, to further increase this or to decrease the number of false positives. But those are already pretty good results, considering that it's a relatively simple heuristic that we implemented to decide on which post blocks to connect to each other. Okay, to conclude this talk, I also want to mention the link extraction. I said that it's also important to be able to study how Stack Overflow content is related to external resources, and what our dataset provides is links found in Stack Overflow posts to external websites or to other Stack Overflow posts. We extracted those from the post, from the markdown source, as you saw earlier, but we also extracted links from public GitHub repositories pointing to Stack Overflow posts. And we extracted links in the Stack Overflow posts just from text blocks, because in code blocks you may have things like XML namespace URL, style sheet files, URLs in strings, in code snippets, and those are not really links to external resources. It's just part of the code snippet. Therefore, in our dataset, the links that we extract are just taken from code blocks. And we use this simple regular expression to extract those links from the markdown content of the posts. So we were able, as of 2018, so it's many more today, over 30 million links in Stack Overflow posts to external websites. And those can be easily queried from the dataset. So this is the example showing the links from the post we looked at in the beginning of this talk. For the other way around, so from GitHub as one example for an external resource to Stack Overflow, we use the Google BigQuery GitHub dataset that allows us to query all public repositories on GitHub using an SQL query and a regular expression. And we again searched for links to Stack Overflow in public files on GitHub. And this resulted in 6 million links. Again, this is 2 years ago. Now it's many more. 6 million links back then to almost 500,000 repositories. And those links pointed to almost 150,000 different posts on Stack Overflow. And again, querying this is pretty easy. Just specify the post, and then you see in which GitHub repositories this post is being referenced. In the case of the example we used throughout this talk, It's referenced in 103 distinct repositories as of 2018. Okay, now that we have all this, now that we extracted post blocks from post versions, linked them to their predecessor, and also extracted links from posts to allow researchers analyzing the relationship of Stack Overflow content, external and external resources. We also did a brief analysis of how the content evolved to show that the dataset is actually useful, that we can retrieve new results, which was not possible with the original data dump, that is not as fine-grained as our dataset. And we found, for example, that posts grow over time when, for example, new code blocks and text blocks are added. I mentioned the example of the introduction of lambda expressions to Java, and then in many posts you just saw that users added an additional code block and an additional text block outlining how a certain task could be achieved using lambda expressions in addition to the already existing solution they had. But we also observed that the individual code blocks are relatively stable, or the size of those code blocks. So the posts usually grow by adding new text and code blocks, not so much by extending the existing blocks. They are modified, the blocks, but they don't really grow that much in size. Posts grow because new snippets are added to the posts. And only in 6% of all edits, the code blocks were changed without also updating text blocks. For example, to document the change that was made to the code blocks. And also interestingly, almost 80% of all edits were made on the same day that the post was created. So the updates, because there's a new language or library version, are actually in the minority. Most of the edits are fixes that are implemented soon after posting a question or an answer. And most of the edits are made by the post authors themselves, which somehow makes sense. If you post an answer on Stack Overflow, you are the one who updates the answer and implements fixes or changes. We also found that comments and edits are closely related, that edited posts have significantly more comments and commented posts have significantly more edits. And we also conducted a qualitative analysis of this relationship. And this is, of course, related to what I mentioned in the beginning of this talk, that often comments are used to report bugs, which are then fixed by editing an answer. And we are still working on this dataset, actually. And there are many different follow-up steps to this kind of research. We are still looking into communication patterns in Stack Overflow, in particular how comments are used for feedback and how the platform could be improved to better display the comments or to better link comments to the edits they trigger. Another direction is to compare the edits shortly after post creation to the edits that are made later. As I just mentioned, edits soon after the creation are most likely minor fixes or in response to the discussion within a post, and then the later edits could be updates, for example, to new language or library versions. I mentioned that most of the changes are being implemented by the post authors, but nevertheless, there are moderator changes to content on Stack Overflow, and studying those typical moderator changes is another interesting direction. Something else we are working on is identifying bug fixing edits. So focusing on the code snippets on Stack Overflow that are now easily available using the ETC-torrent dataset, but identifying the edits to those code blocks that actually fixed a bug, maybe in response to comment. Because then we are able to propagate those changes to projects using the code. So suppose a user a developer on GitHub copied code from Stack Overflow into their project, and then there's a fix on Stack Overflow that fixes an important security issue in the snippet. Then it would be good to have a tool that informs the developer who copied the code that there's a fix, and maybe even allows to automatically propagate the fix to the open source project. And therefore, we first need to identify bug fixing edits on Stack Overflow. This is another direction of this research. Yeah, and the goal is to find buggy snippet version in GitHub repositories and to actually fix them. And also there are still things we can improve in the dataset. For example, detecting code blocks that are not actually being used for code, but for error messages or exemplary outputs that users provide in their posts, and to distinguish those from actual code snippets in Python, Java, or whatever is another direction we are currently working on. Also, the distinguishing between bot edits and edits by users, and further improving the post-block matching is also something we continuously work on. Okay, to summarize this talk, I presented our esotorrent dataset first by describing how we extract post blocks, meaning text or code blocks, from post versions of Stack Overflow posts, then matching them to their predecessors in the previous version of a post. And then finally, we extract links from and to Stack Overflow posts to allow researchers analyzing how snippets on Stack Overflow are related to external resources, and we presented some preliminary results of how content on Stack Overflow evolves. If you have further questions, please feel free to reach out to me by email, Twitter, whatever you prefer. And there's also some more information about the dataset on the website I already mentioned. Okay, finally, to conclude this talk, some takeaways that are not limited to Stack Overflow or the specifics I outlined in this talk. One takeaway is that mathematical notation can be a very useful tool to precisely describe problems and potential solutions. So we introduced all those definitions to be able to specifically describe what problem we have and how we could solve it using the strategy that I presented. Another result here is that more or less simple heuristics can achieve good results, in our case, to match those post blocks to their predecessors, while still being understandable and explainable. So using the definitions I presented and the pseudocode matching strategy, it's very transparent how this strategy works and how decisions are being made. So we don't always need complex machine learning techniques that sometimes work as a black box and that are to some degree not understandable anymore, not transparent anymore. And this talk provided hopefully one example for how far we can get with implementing simple heuristics. So it's not really simple in the end. You saw all the definitions we needed and the notation we needed to precisely describe the problem, but it's still relatively simple and relatively understandable and explainable. And I hope this is a nice insight for you as well. Okay, this concludes the talk. Again, feel free to reach out to me, have a look at the website, and if you have any questions, please let me know. Thank you very much.